Hey, hi everyone. My name is Yona. I'm a PhD student at the Weizmann Institute of Science in Israel, and I work mainly on fairness in machine learning. Today, I want to tell you about this recent project, evidence-based rankings. Good. So as we all know, data-driven or machine learning algorithms are pretty much everywhere, and they are doing a lot of cool things. But every once in a while, we see a headline like this or like this. And it's clear that when we're just applying these tools in sensitive domains without a lot of thought, kind of bad things can easily happen. So there's a lot of interest around fairness these days, kind of how can we formalize what's going on here and how can we prevent this type of bad behavior. So there's a lot of different ways you can address this. My PhD research is kind of taking a more formal, theoretically grounded approach to fairness. And these are kind of the pillars of my approach and theoretical one in general. So the first is that we need to really reason with the appropriate abstractions, right? So we are computer scientists. I can't model every part of the problem. I want to make sure I'm modeling the essence while being general enough to provide kind of general purpose definitions or solutions. The second aspect, and arguably the most important one, is rigorous definitions. By rigorous, I mean mathematical. So definitions that we can write out, we can play around with, and make sure that they're doing what we want them to do across a range of scenarios. The third element is kind of strong protections. So by this, I mean definitions that can provide strong protections even kind of against adversarial behavior or non-well-intentioned actors. And finally, we can talk about provable guarantees, right? So once I have these definitions or objectives, when can I achieve them? Good. So one thing that's really characteristic of this field is that there are many, many different definitions of fairness, and this can be quite confusing at first. One kind of intuition for why this happens is this quote that I like, which is fairness is what's left when unfairness is gotten rid of. And this kind of gets to the essence of how defining fairness is much harder than kind of saying what's unfair. And at a high level, there are two reasons, I think, for the many definitions. The first is context. Okay, so fairness as a concept is very context specific. By this, I mean that the same behavior can be either fair or unfair, depending on the context. Okay, so think, for example, about advertising an ad only to men. Is this fair or not? Well, that depends. If I'm advertising shampoo, that might be perfectly fine. If I'm advertising a job, much less so. Okay, and as humans, we have an easy time reasoning about context. It's much harder to build this notion into algorithms. The second element is the downstream impact. Okay, so I can't really say whether a particular estimate or output is fair if I don't know how it will end up being used. Okay, and this kind of relates to this project, which is thinking about fairness in settings beyond classification and scoring. And in particular, I argue that in reality, a lot of the time, the real motivation for scoring for regression tasks is actually ranking. So for example, think about college admission setup, right? A college is trying to estimate the probability that a candidate will graduate from college given the information that they have about them. In this case, I'm not really interested in this probability per se. I really want to use this to rank the individuals. Okay, so this motivates looking specifically at fairness in the context of rankings. Okay, so I'll start with our model, which is simple but slightly non-orthodox in the sense that there's really a discrepancy between the object of interest and the data that I have access to. So I'm going to assume that every individual has a true probability of success. Okay, so I'm going to denote this P star. But on the other hand, my historical data, the data that I have access to, is only binary realizations of this P star. Okay, so think of a coin toss with, for example, a bias of 0.8. And you can already see that this is a very challenging setup, right? In some sense, I want to rank individuals according to their true probability of success, but without ever kind of observing it directly for a single individual, presuming that I never see multiple realizations of the same individual. Okay, so what's our objective? The perspective that we take in this work is that we want to try to learn a scoring function such that the ranking that it induces doesn't disproportionately harm groups of individuals that we care about. Okay, and you can already see that I'm talking about groups at this point. You might wonder why I'm not trying to give a guarantee towards single individuals. And of course, I'd like to ideally, but again, in our model, I can't really do this, right? The outcome data that I have only provides reliable information about the P star for large enough groups, not for single individual. Okay, and this is true because when I look at the expectation of the binary realizations over a group, I can argue that it's quite close to the true expectation of P star for this group. So I do have an estimate for that. Okay, so all the definitions that I'll talk about will be parameterized by what I'll denote by C, which is a rich and intersecting collection of groups. So for example, women who went to Harvard, people who have kids, etc. And this is kind of inspired and consistent with the recent literature in fairness on between individual and group notions of fairness. Okay, so what do we do in this work? Basically, we define two families of definitions. The first definition is, we call it domination compatibility. Okay, so these are all definitions for a ranking. So a ranking satisfies domination compatibility if intuitively it doesn't rank a more qualified group below a less qualified group. Okay, so kind of this speaks to inversions in the ranking between groups that belong to C. Okay, so this is a very kind of, you can think of it as a semantic notion of fairness in the sense that it's very clear what I'm trying to guarantee towards particular groups. The second definition is slightly more technical, kind of less clear what is the guarantee for a single group. I'm going to call this evidence consistency. And a ranking is said to be evidence consistent if it can be derived by a predictor. So if it's induced by a predictor that has the approximately correct expectations for each of the sets in this collection C. So for every set S in C, the expectation of the predictor P tilde is approximately the same as P star. Okay, and this has an intuitive interpretation in the sense that it speaks to the fact that there is some way to view the world, as denoted by P tilde, which is consistent with the empirical data, with the evidence that I have in hand, and that gave rise to the ranking in question. Okay, so these are two definitions for when a ranking is fair. So just to give you a flavor of the results in this paper, so first of all, we characterize the relationship between these two definitions, and there's actually something quite interesting going on here in the sense that when the class C of sets is predefined, so it can only depend on the features in question, not the ranking, then the second definition is strictly stronger than the first. On the other hand, when C can allow to depend on the ranking in question, so for example, I can add to C sets that correspond to the deciles in the ranking, for example, then the two definitions actually become equivalent. Okay, so the second part is kind of why is this implication interesting? What's the algorithmic implications? And there's actually some useful results. And really, the corollary from what I said before is that if I want to learn a ranking that's domination compatible, that has this strong intuitive notion of fairness, then it's enough to learn a predictor that is sufficiently consistent and then take the ranking that's derived by it. And here, there's actually strong connections to previous works on scoring function. There's this ICML paper that actually defined exactly this notion for predictors, called it multi-calibration, and even gave an algorithm to learn it. Okay, so there's two interesting things here. First, we can have an algorithm to learn domination compatible ranking. And second, this gives kind of a different view to this notion of multi-calibration and why it might be desirable. Okay, great. So just to summarize, basically we considered this setting where fairness was really aligned with accuracy, right? If we could learn P star, great. The problem was that we don't expect that we can learn P star exactly. And then there's this difference between what kind of straightforward machine learning would do, just minimize an average loss, that might not rule out blatant harms to these more structured subgroups. So instead, we directly reason about these more structured subgroups by using this collection C and define evidence consistency, which you can think of as trying to ensure closeness to P star in some particular way that really takes these subgroups into account. And there's interesting open questions that we can talk about over the Q&A if you're interested. That's it. Thank you for listening.